how can a universe built from a small inventory of fields and interactions become so vast, old, complex, and capable of understanding itself?
That is, I mean, that's the ultimate question, isn't it? Because our everyday human intuition is just completely unprepared for the actual answer. We evolved to survive at a very specific, like medium-sized scale. Our senses are tuned to find food, avoid predators, and navigate a world of solid objects moving at relatively slow speeds.
Yeah, the stuff we can actually see and touch.
Exactly. But modern physics reveals a reality that is vastly larger, fuller, and much stranger than our biological senses suggest. And crucially, this deeper understanding doesn't make our ordinary, everyday experience unreal.
It's not like the Matrix or something.
Right. It doesn't mean your desk isn't there. It just extends our perception through sophisticated instruments and mathematics, revealing the hidden machinery beneath the surface.
Exactly. And that is our mission for this deep dive into Frank Wilczek's Fundamentals, 10 Keys to Reality. We are going to completely tear down our intuitive picture of reality and rebuild it from scratch.
I love it.
We're going to start down at the absolute smallest scales, like the quantum fields and fundamental symmetries that make up everything. Then we'll figure out how those tiny, frantic interactions somehow stitch together the very fabric of space-time, energy, and mass. We'll confront the bizarre rules of quantum probability and ultimately zoom all the way out to the sheer scale and age of the cosmos to figure out how cold, hard physical laws manage to create living, breathing, thinking people like us.
It's really a journey from the limits of our unaided senses down into the theoretical bedrock of nature and then back up to the cosmos, basically mapping exactly where established knowledge ends and, the great mysteries begin.
Okay, let's unpack this. Starting with the building blocks. When I look around the room right now, I see thousands of different materials. Glass, wood, plastic, metal, water.
Right.
My instinct is that there must be an incredibly complex, massive catalog of unique ingredients to build all this diversity. How can a universe so incredibly vast and diverse be made of so few fundamental things?
It really comes down to this concept of a small inventory. Modern physics shows us that a remarkably modest set of elementary particles and fields generates literally all the diverse matter we interact with.
Okay.
Think of it less like a massive catalog of unique parts and more like the alphabet. You don't need a million unique symbols to write millions of different books, right?
You just need 26 letters.
Exactly. 26 letters, a few rules of grammar, and the space to combine them in nearly infinite ways. Nature uses a tiny alphabet of basic ingredients like electrons, quarks, photons, and combines them under strict rules to write the entire encyclopedia of reality.
But wait, if everything solid is just these tiny alphabet letters interacting, then the vast majority of everything is just empty space. Like, if I take a steel box, seal it completely, and pump every single atom of air out of it to create a perfect vacuum, isn't that space inside just nothing?
Oh, that is a huge misconception we need to correct right away because it trips up almost everyone. Yeah, empty space in modern physics is absolutely not identical to philosophical nothingness. If you pump out all the air, block out all the light, and cool that box down to absolute zero, you have not created a void.
Wow. Okay.
Space itself is teeming with potential. It is filled with underlying quantum fields and this virtual activity constantly boiling beneath the surface. It's a vibrant, active arena, not just a passive, empty container.
I have to push back on that, though, because if I look inside that perfectly empty frozen box, I see nothing. How do we actually know this space is teeming with activity if we can't see it or bump into it?
Well, that's where we have to explicitly distinguish between our types of knowledge. We have direct observed measurements, which are things we actually capture with massive telescopes or smash together in particle colliders.
Right, the stuff we can definitively track.
Exactly. But to understand the abundance of so-called empty space, we rely on theoretical frameworks. And these aren't just guesses. They are rigorous mathematical models that make incredibly precise predictions.
Like what?
Well, for example, because of this hidden quantum activity in empty space, two uncharged metal plates placed incredibly close together in a vacuum will actually be pushed together.
Wait, pushed by what?
By the space itself. That's called the Casimir effect. The theoretical math predicted it, and then our instruments directly observed it. The nothingness actually pushes things.
That is wild. The empty space is doing the pushing.
Yeah.
So if the universe is built from this small inventory of fields, What actually are the fundamental building blocks? Because the textbook image I have from high school chemistry is a bunch of tiny, hard, classical beads orbiting each other like a miniature solar system. Are you saying those beads aren't real?
Well, what's fascinating here is that quantum field theory completely overturns that image of tiny, hard beads. Fields are primary in modern physics.
Right.
The universe isn't a collection of marbles, it's a collection of infinite, overlapping fields that stretch throughout all of space. What we call a particle, like an electron, is actually just a localized excitation.
And excitation, like a ripple.
Exactly. It's a little ripple or a concentrated vibration in the underlying electron field.
So an electron isn't a tiny object moving through a field. The electron is the field vibrating in a specific spot.
Precisely. Imagine plucking a guitar string. The note you hear isn't a physical object you can hold. It's a property of the string's vibration. Particles are the notes played on the underlying quantum fields.
That's a great way to put it.
And the rules that govern how these fields vibrate and interact are guided by symmetry. In physics, symmetry is essentially a transformation that leaves a physical description unchanged. It's the ultimate mathematical guide to discovering physical laws.
I want to make sure I'm following this. When you say symmetry, my mind goes to geometry. Like, if I have a perfectly smooth, round sphere and I close my eyes while you rotate it, when I open my eyes, I can't tell you moved it. It looks the exact same. Is that the kind of symmetry we're talking about?
Exactly. The laws of physics don't change if you rotate your laboratory or if you move it from New York to London, or if you wait until tomorrow to run the experiment. The laws themselves possess deep symmetry.
Okay, that makes sense.
But here's the catch. The universe we actually live in doesn't look perfectly symmetric. It's highly structured, messy, and diverse.
Right. I'm not a smooth sphere.
Yeah.
The Earth isn't the same in every direction. We have mountains and oceans and completely asymmetric shapes everywhere.
Which brings us to one of the most beautiful mechanisms in physics. It's called spontaneous symmetry breaking.
Spontaneous symmetry breaking.
Yeah. This is how perfectly symmetric equations can produce less symmetric structured physical states. Let's step away from physics for a second. Imagine a large, perfectly round dinner table set for 10 people.
Okay.
Between every single plate is a water glass. The setup is perfectly symmetrical. No glass specifically belongs to the plate on its left or its right.
Okay, I can picture that. A perfectly symmetrical dinner party waiting to happen.
Right. But it's an unstable state. The moment one guest sits down and reaches for the glass on their right, the symmetry is instantly broken.
Oh, I see.
Now, to avoid drinking from the same glass, every other guest must also reach to their right. The underlying rules of the table didn't change, they are still symmetric, but the actual physical state of the dinner party is now locked into an asymmetric structure.
Oh, wow.
That is how structure emerges in the universe. Symmetric laws spontaneously drop into asymmetric physical realities.
That makes total sense.
Mm-hmm.
The rules allow for anything, but once the universe makes a choice, the structure locks into place. But if everything is just ripples and fields and broken symmetries at a dinner party, what is actually holding it all together?
That's the million-dollar question.
Because my desk, my body, the microphone in front of me, they feel remarkably solid for being made of vibrating fields.
To understand that solidity, we have to look at quantum chromodynamics, or QCD. This is the theory of the strong interaction, which is the force governing quarks and gluons deep, deep inside the atomic nucleus.
Okay, so quarks are the ripples that make up protons and neutrons.
Yes. And there are two mind-bending mechanisms here. The first is confinement. You can never isolate a single quark. They are permanently bound together, usually in triplets.
Wait, why can't I isolate one? If I have a really, really tiny pair of tweezers and I grab a quark and just pull it away from the others, what happens?
That brings us to the second concept, asymptotic freedom. It's incredibly counterintuitive. With gravity or electromagnetism, the further away two things get, the weaker the pull between them.
Right, like magnets.
But the strong interaction works completely oppositely. At incredibly short distances, when quarks are right next to each other, the force actually weakens. The quarks are almost totally free to wiggle around.
So they're totally fine as long as they stay close.
Yes, but the moment you try to use your tiny tweezers to pull one away, the gluon field between them stretches and forms a flex tube. The tension grows massively, like stretching an incredibly tough rubber band.
Oh, okay.
The further you pull, the more energy you put into that stretched rubber band. Eventually, the tension is so high that the rubber band snaps. But here's the twist. The energy released when it snaps is so immense that it instantly creates brand new quarks on the broken ends of the rubber band. You don't get an isolated quark, you just created a new pair.
Wait, I pull them apart, the energy builds up, and instead of separating, the energy just manifests as more physical stuff.
Exactly. And this leads to one of the most profound aha moments in all of physics. I'm sure you remember when the Higgs boson was discovered and the media hailed it as the God particle that gives everything mass.
Or absolutely, it was everywhere. The Higgs field is what makes matter heavy, right?
That is another major popular science myth that we need to naturally correct.
Wait, really? It doesn't.
Well, the Higgs field is famous, and it does explain the mass of individual fundamental particles, like electrons and individual quarks. But those isolated quarks hardly weigh anything.
Oh, I didn't know that.
Yeah, the vast majority of the mass of ordinary protons and neutrons, which means 99% of the mass of your body, the Earth, the stars, it does not come from the Higgs field. It arises from the sheer frantic energy of the strong interaction.
So my mass isn't because the particles inside me are heavy. My mass is just energy.
Yes, E equals mc squared. Energy and mass are deeply relational, interchangeable concepts. The kinetic energy of those quarks zipping around near the speed of light, and the binding energy of those glue-on rubber bands constantly stretching and snapping inside every proton in your body, that furiously contained energy is what gives you almost all of your physical mass.
That is incredible.
You are heavy because you are a contained storm of energy.
Here's where it gets really interesting. Physicists have been incredibly successful at categorizing all these particles, fields, and strong forces into a framework called the Standard Model. It sounds like we have it all figured out. Is the Standard Model the ultimate answer? Have we essentially cracked the code of reality?
We have cracked a code, but definitely not the code. The Standard Model is arguably the most successful, highly tested scientific framework in human history.
Wow, okay.
It organizes the known elementary particles and 3 of the fundamental interactions perfectly: electromagnetism, the strong force, and the weak force. But we have to be ruthlessly clear about its strict limits. It is a phenomenal map, but it is incomplete. For one, it does not include a complete quantum theory of gravity.
Which seems like a pretty big omission, considering gravity is what holds the planet together.
It's a massive omission. The Standard Model also doesn't resolve enormous cosmological mysteries, like dark matter or dark energy. It completely ignores them.
Why do physicists rely on it so heavily if it ignores gravity and dark matter? Doesn't the math look ugly if it have massive holes in it?
Actually, the math of the Standard Model is incredibly elegant. But a successful model is not a literal, comprehensive picture of all reality. It has a specific domain where it works beautifully.
I see.
Sometimes, physicists get seduced by mathematical beauty, hoping an elegant, perfectly symmetric equation is the final, universal answer. But while mathematical beauty is a wonderful guide for discovery, it can never replace experimental evidence. Nature gets the final say. If the math is beautiful but the experiment contradicts it, the math is wrong for that domain.
And nature gets pretty intense when we zoom out from the quantum domain to the macroscopic scale. We've been talking about the microscopic storms inside atoms. Now let's talk about gravity in the cosmos. If gravity isn't in the Standard Model, how do we explain it?
This is the domain of Einstein's general relativity, and this requires another total shift in intuition. Gravity isn't just an invisible rope pulling objects together through an empty void. Gravity is geometry. It is dynamical space-time.
Geometry, so it's about the shape of space, not a pull.
Exactly. Think about flying an airplane from New York to London. If you look at a flat paper map, the flight path looks like a huge curve. But if you look at a globe, you realize the plane is actually flying the straightest, shortest possible line over a curved surface.
Oh, that makes sense.
Space-time is like that globe. Massive objects like the sun warp and curve the very geometry of space and time around them. The Earth isn't being pulled by a rope, it's simply traveling in the straightest possible line through warped geometry. Matter tells space-time how to curve, and curved space-time tells matter how to move.
Which gives us the stage for cosmic history. Space itself can bend and stretch and expand.
And it is expanding, starting from a hot, dense early phase we call the Big Bang. And with that cosmic expansion comes a very crucial concept, entropy and the arrow of time.
Okay, entropy.
At the microscopic scale of quantum fields, the laws of physics are generally reversible. A movie of an electron scattering off a proton looks perfectly normal if you play it backward. But macroscopic laws, the laws governing large collections of things, are strictly irreversible.
This is the classic idea that things move from order to disorder.
Yes, but let's avoid the cliché of scrambling an egg. Think about a drop of dark blue ink falling into a glass of pristine water. At first, the ink is a highly ordered, concentrated little sphere,
Right.
but over time, the ink particles bounce around and disperse until the entire glass is a pale blue. The rules of physics do not forbid those dispersed ink particles from randomly bouncing back together to form a perfect drop of ink again. But statistically, there are billions of ways for the ink to be mixed, and only one way for it to be a perfect drop.
So it's not that the universe wants to be messy. It's just a statistical inevitability.
Yeah.
The ink is never going to unmix itself.
Yeah.
And that statistical certainty is what gives time its forward direction.
Exactly.
But looking out at that expanding universe moving toward disorder, how much of it can we actually see? Are we looking at the whole picture?
We are only looking at a fraction. Our observable universe is strictly bounded by cosmic horizons. Because light takes time to travel and the universe has a finite age, about 13.8 billion years, we can only see the parts of the universe whose light has had enough time to reach our telescopes.
Right.
What we observe is not automatically the whole universe. It's just our local patch. There could be infinitely more universe beyond that horizon, but it is fundamentally cut off from our view.
Okay, so we have this beautiful, predictable macroscopic universe governed by gravity, curving space-time, and the relentless forward march of entropy. But if we leave the stars and go back down to the quantum realm, things get completely, deeply unintuitive again.
Oh, yeah.
Because everything at the bottom is based on probability. If the quantum world is fundamentally uncertain, does that just mean anything is possible? Like if I walk into a wall enough times, will I just magically phase through it? Is the universe basically magic?
No, absolutely not. We must firmly address this misuse of quantum mechanics. Uncertainty does not mean all claims are equally plausible or that anything goes. It is not magic. In fact, quantum theory predicts probability distributions with extraordinary accuracy. It is incredibly precise.
So it's not random chaos. It's a very precise measure of uncertainty.
Yes, we know exactly the probability of an event happening. And this relies on a deeply profound concept called complementarity. It's the idea that different experimental arrangements can reveal mutually limiting aspects of a system.
Mutually limiting. How does that work?
Think about a piece of music. You can look at the sheet music, which tells you the precise pitch and frequency of every single note, or you can listen to an audio recording, which tells you exactly when the sound happens in time.
Okay.
But if you take a tiny millisecond slice of that audio recording, a single moment in time, you can't determine the pitch because pitch requires time to oscillate. You can't measure the exact pitch and the exact millisecond it occurred simultaneously. They are complementary descriptions.
So they don't make reality logically inconsistent. They just show that our tools force us to choose which aspect of reality we want to measure, and we can't measure every property at once.
A perfect analogy. And importantly, we need to correct the mystical interpretive leap that sometimes crops up in pop culture here. Human consciousness does not create physical reality.
That's good to hear.
The measurement problem in quantum mechanics is a highly technical debate about how quantum states interact with macroscopic instruments. It is absolutely not an invitation to say our minds magically conjure the physical universe into existence just by looking at it.
Okay, thank you for clearing that up because that always feels a little too mystical. But that raises an even bigger question. If we are not magical observers conjuring reality, then how does a living, breathing, thinking human come from this cold, calculating physics? If I am fundamentally just quantum fields, broken symmetries, and probability distributions, how does life happen? How did physics invent biology?
Through the concept of emergence. This is the idea that higher-level organization, like complexity, life, mind, can naturally emerge from simple physical ingredients through repeated lawful interactions, environmental feedback, and selection.
So biology is an illusion. We aren't just physics.
Biology is absolutely real, and it has its own rules. Higher-level biological explanations remain completely valid and useful, even though we are ultimately made of quantum fields. You don't need to describe the quantum state of every single electron in a heart cell to perfectly understand how a heart pumps blood. Life uses energy. It processes information, and it relies on complex chemistry, all without requiring any supernatural exemption from the laws of physics. The simple rules of the small inventory compound over billions of years into incredibly complex systems.
So what does this all mean? We have gone from the tiniest quarks wiggling furiously inside a proton to the expanding cosmos bending under the weight of galaxies. In the grand scheme of things, we are just these incredibly tiny, fragile physical specks governed by fields and entropy. Why should we care? Does our physical smallness mean we are completely insignificant?
Well, if we connect this to the bigger picture, our physical smallness doesn't limit our intellectual significance. Yes, biologically, we occupy a very narrow band of scale and energy, but our knowledge allows us to represent, model, and comprehend these vast domains.
Yeah, that's true.
We have managed to embody our abstract understanding of quantum fields into physical technology like lasers, semiconductors, global navigation systems. Our minds, built from the universe's small inventory, can turn around and successfully map the cosmos.
And there is a very real, rigorous scientific method to how we do this mapping. It's not just philosophical guessing.
Exactly. Reliable knowledge grows through careful measurement, rigorous mathematical modeling, and brutal error analysis. And doing that requires profound scientific humility. We have to admit when our intuition is wrong.
Which is hard.
It is, but we must be careful here because scientific humility does not require refusing firm conclusions. Some people think being scientific means saying, oh, we can never know anything for sure. That's wrong. Scientific humility means having calibrated confidence.
Calibrated confidence.
Yeah.
We're incredibly firm where the experimental evidence converges, and we remain openly curious where it doesn't.
Precisely. We constantly distinguish established, observed knowledge from what is currently model-dependent or heavily speculative.
Which leaves us with some truly thrilling, open problems on the frontier.
The universe is full of them. We are actively hunting for dark matter, which we can detect gravitationally but completely fails to interact with our light-based instruments. We're trying to understand dark energy, the mysterious force accelerating the expansion of the universe.
And axions, right?
Yes. We are looking for hypothetical particles like axions, which are a great example of disciplined speculation. Using gaps in theoretical consistency to motivate very specific, highly targeted searches.
And of course, we are still searching for that holy grail, a complete theory of quantum gravity. We need to somehow unite the beautiful rules of the standard model with the curving space-time of general relativity, not to mention figuring out the exact initial conditions of the Big Bang itself.
The frontiers are wide open. The small inventory created a vast, rich reality, and we are just barely beginning to map the edges of it.
And map it, we will. Before we wrap up today's journey, we want to make it absolutely clear that this deep dive is an independent Cosmora HQ book overview and is not an official or complete audiobook. We highly encourage you to seek lawful access to Frank Wilczek's Fundamentals, 10 Keys to Reality through the publisher, your local booksellers, libraries, or authorized services.
It is a remarkable journey of disciplined thought, and reading the source material directly is incredibly rewarding. There is so much more depth to explore.
We would love to hear your thoughtful engagement on these concepts. Thank you for taking this journey with us and letting us completely rebuild your reality. We're going to leave you with something profound to mull over on your own. What does modern physics reveal about reality that everyday experience hides from us?